Come on in, sit up front. It's just us, and it's not a Hadassah event. No one's going to ask you for money, so if you want to move closer, that's fine. I just want to say quickly, how many of you have ever read or heard of this paper? Has anyone ever read or heard of this paper? You have. Okay, so you probably know the punchline to the first part. So just hang tight with me for a little bit. So from Usenik's HotOS 15, there was this really interesting paper called Scalability, but at what cost? And this paper has haunted me. This paper has haunted me for a lot of reasons. Namely because although distributed systems are kind of my thing, just like everybody else, I get my butt kicked by them, right? So we have these questions like, why can scaling make things slower, right? And shouldn't throwing more compute at a big problem actually make it faster? Like, shouldn't you be able to throw more resources at a problem and have it get faster? And if you think that these questions are interesting, you're definitely in the right place today. So I just wanted to say thank you so much for coming. It's really great to see you all, and I'm thrilled to be here. I'm Jonathan, and I like distributed systems. And even that said, in the age of microservices, I am on team monolith. And that was, by the way, the closest I could get to the 2001: A Space Odyssey monolith. And this one is kind of shiny, which I think is an upgrade, really. I mean, if you just have to consider it. So I'm on team monolith, but we can also ask ourselves why. And we can ask ourselves why I'm on team monolith. We can say, why do things slow down like this? And we can say, why am I on team monolith? But we can also ask, by putting these problems into context, we can say, why can't we do better? And so when a problem outgrows a single computer's processing capacity or storage capacity, we tend to move it onto multiple computers. We don't really have a choice in many cases because it's outgrown a single computer's processing capacity and storage capacity in a way that's cost effective, okay? So what the authors of this paper, this cost paper did is, for those of you who've read it, you know, they created this really cool little word, configuration outperforming a single thread. Okay, configuration outperforming a single thread. So port yourself back a decade to 2015, which is almost a full decade ago, all right? Anyone remember 2015? Because I do, okay. So specifically, wind back the hype machine. I used the slot machine emoji because, you know. Before AI and large language models were all the rage, right? Before blockchain was the rage for a while, right? There was, say it. Big data, remember? All right, well, sorry, what were you gonna say? It was probably good too. You were gonna say microservices. Okay, great, all right, so definitely possible, right? But big data, right? Like everyone was saying, data is the new oil, like, and looking at you like you were a moron. Like, didn't you hear the news that big data is the new thing? So, everyone's building these big Hadoop clusters in like broom closets and stuff, right? Just trying to, figure it all out. And around this time, this cost paper was researched and written. It was written amidst this big data hype that I think that we all remember. So why am I starting off a talk with this? Why is this paper interesting? Okay, and it's interesting because it challenges the conventional wisdom of just throw more execution substrate at it, which is typically something that we do, right? The authors tried a bunch of graph algorithm and problems and et cetera, and they tried it on both single node that were really heavy and distributed setups, okay? Who knows what happened? Who can guess what happened, right? Who thinks it got better with more machines? Who thinks it got better? All right. Totally true how you define better. I don't know what better means. Better should have been in quotes, right? Who thinks it stayed the same more or less with more machines? And who knows exactly where I'm going and thinks that it got worse with more machines, right? Okay, so there we go. We have that it got worse. Well, it got worse with more machines. And we found that more threads doesn't automatically mean faster. We found that more machines doesn't automatically mean faster. And this leaves us in an interesting predicament because now we have a problem that's too big for one machine, and it gets slower when we throw more machines at it, all right? Everyone talks about how hard it is to scale systems. Few discuss why that is. Few people will sit down and say, like, actually, this is really hard to do, and here's the reason why. It turns out there are real computer science reasons why it's so challenging. This paper explores it. Highly recommend that you read it, although I did just kind of give away the punchline. All right? So here are 2 helpful guidelines from this paper, right? This is how the authors close up this paper, and they say for largely disjoint populations. Guideline 1, if you are going to use a big data system for yourself, see that it is faster than your laptop. If you are going to build a big data system for others, see that it is faster than my laptop. I love this advice, right? This is great advice. And it has nothing to do with MapReduce. It has nothing to do with, in particular, parallel compute. It has nothing to do with any of these things that we may think that it has. This is great advice, right? Because of practical reasons. Because sometimes when you throw things at a problem, more resources make it slower, which is really counterintuitive and, please take my word for it, really frustrating also. It's really, really frustrating, okay? For most problems, you can't just throw substrate at it, whether it's single node or distributed. You can't just throw more execution substrate at it. You can't. So I'm gonna make an assertion, and this assertion is based on this paper, is that coordination makes systems slower. Specifically, coordination makes systems slower. And I wanna be clear, I'm talking about systems. And I said slower. Not slow, slower. So let's take a look, all right? Systems, meaning all types of systems. We've learned from operations research, right? Organizations are systems which can get slower. How many of you have seen top-down command and control structures, right? When you try to rigidly enforce how every team works in an organization, things don't get faster, things don't get better, they get usually slower, right? That coordination. Okay? And notice, by the way, I said slower, as I said, and not slow, because it just produces degradation in performance and throughput, not necessarily tanking it, although sometimes it can, believe me, and that's way entertaining and way frustrating when it does happen. How many of you have ever thrown computers at it and it's just ground to a halt? Has anyone ever experienced that? Just show of hands real fast, because I see some hit. Okay, so more of you than I expected, probably about a third of you. So I said slower and not slow, okay? Reiterated, coordination makes systems slower. Adding more processors means more time spent coordinating the work across those processors. And more time spent coordinating is less time spent doing actual work, solving the actual problem you have to deal with. So now we can start building a mental model. We have the foundation that we need to start building a mental model, all right? So together, let's invent a new term to name what we're reasoning about. They brought you cost. We in this room are bringing you Scale-Originated Coordination Overhead, or SOCO. I'm told it's trademarked. Please don't tell, all right? So SOCO, right? Scale-Originated Coordination Overhead. So we can identify some levels with this mental model of SOCO. We can say there's the level where you have one CPU, one core, which used to be all you had, because if you're old enough to remember the days before symmetric multiprocessing, that's all you had, you just had one core, right? So we have the level of one core, one CPU. We have n CPUs where n is greater than 1. Then we have one machine. Then we have the level where there are n machines. You can see where I'm going with this, right? Where n is greater than 1. And in fact and indeed, we have some transition points, and this is key. You have going from n equals 1 to n is greater than 1 CPUs, and you have another transition point where n is 1 to n is greater than 1 machines. These transition points, right, when you cross them, that's where SOCO can start to appear. Because suddenly, you're not working on one machine, you're working on multiple machines, or one thread anymore, right? You have multiple processors, and you usually, not always, we're gonna talk about which cases are which, usually have to coordinate between them, okay? But it really depends on the workload, which is a total computer science thing to say, right? Like, oh, you know what the answer to the question is? Well, it depends, right? Which we all bust out from time to time. So why does it depend? Let's talk about it, let's go through it. Why does this depend? Well, it depends because coordination is there to enable some sort of synchronization. Sometimes you're using locks, sometimes you're using other things, but some sort of synchronization. This, however, is on a single machine. In a distributed environment, Coordination is not there to enable some sort of synchronization. Coordination is there to enable some sort of consistency. Which, keep in mind, because we're going to talk about how they're two sides of the same coin. Right? We have plenty of distributed consistency algorithms. Can anyone name, just shout them out, some of the greatest hits of consistency algorithms? Paxos, number one on the list, the granddaddy of all. There's only a few people I've ever met in my life who actually understand Paxos, and that doesn't include me. Paxos, what else? Raft, fantastic. Anyone know Zab? Zookeeper Atomic Broadcast, right? We have Raft there, and then we have like two-phase commit and three-phase commit and friends, like that, all right? All of these work really well at keeping consistency, which is usually another word for agreement. They work really, really well for keeping consistency in distributed environments among different systems. They all work really, really well. One problem, they also all slow things down because they introduce SOCO. Because that synchronization, that consistency, is a form that requires coordination. It implies coordination. Okay? What if, hypothetically, what if we could sidestep the coordination and consistency problem? What if we could entirely just push it to the side, or we could step around it? What would that be like? That would be a nice world, right? If system components could operate independently and without coordination, that would be huge. It would be huge. And the truth is, some problems allow this naturally. Let's look at one, and I'm telling you it's simple example of a problem that allows this naturally. All right? And that would be commutative operations on integers. Everybody's favorite thing, right? I mean, I see all the smiles coming out now. You guys are like, commutativity, rah! And I'm right there with you. So is this big enough? Can anyone see this? Big enough? All right. How many of you have ever seen Rust before? Rust? Okay, a bunch of you. So I'm going to step through it just line by line. So here we have, it's a function just called add5 and sum. It takes a vector, which is like a growable array or a list in some languages of integers, and it produces one integer. We take all our integers and we want to iterate over it, so we convert our vector into an iterator, so we get a view into it, right? We then use map, which is a functional programming construct where we add 5 to each integer in the collection, all right? And then we reduce that by summing it up by doing x plus y, right, into a single integer. All right. So that's our code. And in Rust, parallelizing this code is actually trivial, which is surprising. This is the delta. You take out iter and you put in par iter for parallel iterator, right? It's beautiful, isn't it? This wonderful little library called Rayon. And by the way, my fellow Rustaceans, please don't give me a hard time about not using the sum piece. I know I didn't use sum. I understand that I just spilled water all over my coat. But I also understand that I used reduce because I felt like it would be a little bit more dramatic. So just don't give me a hard time about that. Why does this code parallelize so easily? Why does it parallelize so cleanly? What about it makes it this way? And it was what you all got excited about. Commutativity. Because 1 plus 2 plus 3 equals 3 plus 2 plus 1. Keep this in mind. Order doesn't matter, right? Addition commutes over the integers. Please keep it in mind. We're going to come back to this. Order doesn't matter. So these computations can easily happen in parallel. If the data set is too large to fit on one machine, as in this situation that we're talking about, these computations can easily be distributed. Again, because they are commutative. And there's nothing to coordinate. Ergo, no SOCO. For an in-depth look at this, if you're interested in this topic, there's a really great language level exploration of this called Distributed Pure Functions from Systems Distributed 24 by my friend Richard Feldman. It's a really great talk. He's the creator of the Rock programming language. Definitely want to take a look at that. Most real-world problems are more complicated than adding numbers. Agree? I think we would all agree, right? Yeah, much more, okay? And I'm saying most, I'm not saying all of them, but most of them. This talk isn't supposed to be about what we can't do. This talk, I want us to explore what we can do. And we can do a lot. So what have we learned so far? So far we've learned cost. Just throwing substrate at it doesn't work like we wish it did. It doesn't work because of SOCO, Scale-Originated Coordination Overhead, the term that we invented. Most real-world problems are more complicated than adding numbers. So where do we go from here? Well, there's an emoji for that. And there's also, as it turns out, a paper for that. From 2020, Keeping Calm When Distributed Consistency is Easy. Anyone familiar with this one? Yeah, it's hot, all right? So our path now is we're pivoting from cost to calm, right? We can learn, and I mean it, a lot from this paper, okay? We can learn a lot from this paper. This paper introduces a great example, roads and traffic lights, which I never really thought of as a form of coordination before, but they are. They are a form of coordination, right? This is an example of coordination and it slows things down. Because, why does it slow things down? Because you have 50% of your cars waiting at any given time. Okay? Think about it. They're just not moving, right? You have your east-west traffic, which can be going, or you have exclusive or you have your north-south traffic, which can be going. So they bring in this really cool, really helpful example. There's also a coordination-free alternative, right? Imagine that same roadway, but that network has overpasses so that streams of traffic can just keep driving. I love that. Right? This introduces a great possibility, structuring problems so that they don't need coordination. Okay, so how do we identify problems and solutions which simply don't need coordination? Well, the Calm paper, they ask the same thing. What is the family of coordination-free problems and what problems lie outside that family? So at least we're validated. At least the question that we're asking now is the question that the authors asked years ago. And by the way, if you've heard of the FLP impossibility result and you've heard of the CAP theorem, get ready for the Calm theorem, consistency as logical monotonicity. And the reason for that is because if there's one thing that we distributed systems folks love, it is a cool theorem with a cool abbreviation. We are just so cool. You can tell. The authors say monotonicity is the key property underlying the need for coordination to establish consistency. Consistency as logical monotonicity. A problem, this is the theorem, a problem has a consistent, coordination-free, distributed implementation if and only if it is monotonic. Right? This is great. Monotonic. If we could just write monotone software, it would all be perfect, right? If we could take every problem and structure it like that. I'm excited. Are you excited? I'm excited. Also, what? That doesn't help me, but the authors do a really good job of providing practical definitions. Non-monotonic problems are order sensitive. The order in which they receive information determines how they toggle state back and forth, which can in turn determine their final state. We all know those sorts of problems, right? They're the hard kind. They're the not adding integers together problems, right? Let's take a look at this. Example of a non-monotonic problem, ATMs. By the way, how many of you have ever, excuse me as I digress for a moment. How many of you have ever opened up a textbook, a database textbook, let's just say hypothetically, and they're like, you know what ACID transactions are good for modeling? ATMs. And you're like, wow, that's a great example. And then you think about it and you're like, wow, that's a terrible example. And the reason is because they're not actually synchronous, they're distributed systems ATMs. And no one wants to stand at their ATM for 2 minutes while you wait for the request for cash to come out. They're just going to kind of do it asynchronously. So that always bothers me. But they're wrong for using ATMs. We're right for using ATMs. So just, okay. You have a shared debit card. In this universe, you have a shared debit card. When someone withdraws more than the account holds, the account gets penalized with a $35 charge. Overdraft fee, right? Now let's imagine what a day's worth of charges could look like. So, where's my mouse here? All right, so we have our imaginary ATM log. Our starting balance is $250. We put in $29. Then we take out 200, we're down to 79. Then we take out 33. Then we take out 53. Suddenly, we're in the red. Immediately, we get an overdraft fine of $35. So now we're even more in the hole. Then we deposit 75 at around 10:30 in the morning. 10:49, we deposit another 39, right? And then at 10:49, also someone simultaneously deposits $128, which brings us to 200. Now the truth is this transaction sum, right, as $235, if you were to take all of this and then you remove the $35 overdraft fee, right, you would see that $235 is greater than zero, therefore it is not overdrawn. So if you immediately tally things up and you say, are you in an overdraft state ever, versus like at the end of the day, did you overdraw, right? Then suddenly you get two different answers. In one situation, you deserve a fine. In one situation, you don't deserve a fine. The bank will obviously pick the one where you do deserve a fine so that they get $35 out of you, right? Order matters. Therefore, it's non-monotonic, which is what we wanted to show. By the way, at GOTO, they have lots of math and sometimes in talks, and that was just it. But what about the other sorts of problems, okay? What about the other kind? What about the kind which actually can be solved this way? The paper teaches if message arrival order does matter, it's non-monotonic. If message arrival order doesn't matter, it's monotonic. Order dependent, right, non-monotonic problems, may have to wait for new information to arrive. This waiting requires coordination. That's the waiting part. It is coordination. Order-independent monotonic problems do not need to wait and don't need that implicit coordination. The COM paper authors say, intuitively, monotonic problems are, quote unquote, safe in the face of missing information and can proceed without coordination. So where does this get us? We have this notion of problems that we can safely ignore coordination and problems where we can't. So what we know so far, given this problem that is too big for a single machine, cost, just throwing execution substrate at it doesn't work like we wish it did. We learned this. It doesn't work because of SOCO, Scale-Originated Coordination Overhead. Coordination, consistency, and monotonicity are different facets of the same gem. The COM theorem teaches us to sidestep coordination by structuring systems so that order doesn't matter when possible. So let's get practical for a second. What tools are available to help us design and build calm software systems? Well, the researchers behind this paper invented this thing called Bloom. This Bloom language has a prototype in Ruby called Bud. Get it? Bloom, Bud. Loved it, right? Bud. It looks a little like this. I don't know if you can see it. It's a chat protocol. It's, got a state block, and you don't really need to know what it looks like. It's just using Ruby syntax, right? Here's what the next piece of it looks like. This is the chat server. It includes that chat protocol. You have state, then you have a Bloom thing where it sort of abuses the heck out of Ruby syntax with transitive closures and other things, right? You don't need to know what this does. You just need to take away from it that it is very declarative, right? So their approach at this was very, very, very declarative. Now, I found this code, and I read through, I used to write a lot of Ruby. I found this code really impenetrable. And also before you get all excited, because I can tell you're like, oh wow, I can't wait to write Bloom. You're like, the last Bud commit was also 4 years ago, okay? So, fine. But this gravitation to declarative programming, this really declarative syntax, this still teaches us something, and it introduces a new term called disorderly programming. I love this term, okay? Disorderly programming. Traditional languages like Java and C are based on the von Neumann model where a program counter steps through individual instructions in order. Sounds familiar so far, right? Okay, distributed systems don't work like that. Yes, it's true, they don't. It sucks, right? Much of the pain in traditional distributed programming comes from this mismatch. Programmers are expected to bridge from an ordered programming model into a disordered reality that executes their code. This is taken from the introduction to the Bud documentation, which is their implementation of Bloom from the people who wrote the Calm theorem paper. This mismatch is a huge deal. This mismatch could be a talk in and of itself, right? There's a lot to explore here because now you have a place where you're writing code according to one mental paradigm, and it executes in a completely different paradigm, right? And that mismatch causes a lot of problems. That's like the root of all of our problems, really, when we deal with distributed systems. Time and order and all these things we're talking about, they all come from this mismatch between ordered programming and disorderly programming. When you have the language model, when you have this language model and it doesn't match the system model, that is incredibly impactful and incredibly destructive and really, really hard to deal with. If you are like me and you have ever run into this problem, I feel for you. I'm so sorry. It's hard, right? So yeah, in that case, you're going to prefer declarative over imperative programming. When you can't reason about the order of your system necessarily, but you still have to write it, you're going to prefer declarative over imperative programming. You will. So what are some other options, right? We talked about how Bloom isn't going to be it for us. So what are the other options? Well, the other options are that Bloom was actually a successor to, anyone know? I know you are all chomping at the bit to say it. Dedalus, right, which is a 2011 paper about an experimental system from the same authors that was about Datalog and time and space. Anyone know Datalog? Anyone know of Datalog? Show of hands. A little bit. Oh yeah, hey, there's my guy. What's up, man? How you doing? So, okay, 2 people in the room, right? 2 people in the room. So our path so far has gone from cost, we pivoted to Calm, and now we're going to Datalog. What is, by the way, that's a log. What is Datalog? It's a declarative logic programming language. It's a syntactic subset of Prolog, if you've ever met the granddaddy of all of these logic programming languages. There's a great book online. I put a link to it just on the slide. They're going to make the PDF of these slides available. It's called Facets of Prolog. It's a really great intro to programming in logic programming with Prolog in particular. Highly recommend it if this is something that interests you. If it doesn't, then you can totally ignore this piece. It uses what's called a bottom-up evaluation model. I believe that this log is from the bottom of the tree, which is why I picked. I'm kidding. I have no idea. I'm not a lumberjack. And Datalog programs consist of 2 things, facts, all right? So you have facts there, statements that are held to be true, and you have rules, which are mechanisms to deduce new facts. Really simple. So let's take a look at a little bit of Datalog. This is using the Racket Datalog syntax, which introduces a third thing called a query, all right? So specify a graph with facts. You can see we have an edge, A to B, edge B to C, edge C to D, and edge D to A. So a 4-node graph, all right? You specify a rule, which is a path. You say this is how you get a path. Either it's an edge or a path, and it sort of recursively does it. And you can see that this is a piecewise on line 8 and 9. You can see this is a piecewise declaration. So you're defining it a little bit at a time, and then on line 12 you have a query. So you're saying, hey, show me all the paths. Show me all the paths between any 2 x and y. All right? And this graph is what it describes. You can see A is connected to B is connected to C is connected to D is connected back to A. And this is the query output. It gives you all the possible paths according to its recursive definition. Okay? So it gives you all the possible paths according to its recursive definition, right? So I guess you could say it seems that declarative data-oriented programming can be a calming influence. But how? These are also logs. What about parallel data log? Well, there's Souffle, which takes a data log-like language and converts it to C++, which runs in parallel. What about distributed data log? Well, for those of you who are fans of Clojure, you'll probably already know about Datomic, which embeds Datalog as its default query language for this distributed database, right? What about analytics? Well, there's this really cool thing called Percival, which runs in your browser. It's WebAssembly, and it lets you do reactive Datalog exploration of all kinds of different data, really cool. You can try it out online, called Percival.inc. Very fun, nice way to mess around with Datalog. There are a couple other Datalogs that run in your browser. There's DUSA, there's a bunch of other ones that are really cool, okay? And by the way, that's from the, have you tried rubbing a database on it? That is the best abbreviation. It's like, hi trad boy, so just Datalog isn't enough. I love computers, I'm sorry. Just Datalog isn't enough. And not even distributed Datalog is enough. Because if it were enough, we would all be using it already. So what would be enough? And for this, we're going to make one last pivot. From Datalog to Dataflow, there is another paper, or another presentation, excuse me, at Have You Tried Rubbing a Database on It, 2022. Highly recommend you watch this like 15-minute YouTube video if you get a chance at some point this week. It's really cool. Incremental stream processing with DDlog. DDlog is differential data log, which is a differential data flow library, and it basically allows you to use data flow programming in a distributed environment. What is data flow programming? Well, it turns out that we all know data flow programming from spreadsheets, right? And you can see this really cool spreadsheet here, January, February, then you have Maruary, Aprilary, Mayuary. Excel is a marvel of software engineering. But you can read about data flow programming on Devipedia or Wikipedia. In fact, I'll quote Wikipedia. Data flow programming emphasizes the movement of data and models, programs as a series of connections. Explicitly defined inputs and outputs connect operations which function like black boxes. An operation runs as soon as all of its inputs become valid. So it allows you to declare this is how you wire it up, and then the data flows through it. So really, we want to talk about distributed data flow programming, which in fact and indeed has its own article on Wikipedia also, right? But we're talking about a way that we can functionally compose operations to build a data flow, which is sort of the plumbing, the piping. And these four combinators are what I call the 80-20 combinators, because they're the 80-20 of functional programming. They're the 20% that give you 80% of the fun, right? Map, filter, reduce, for each. That's my term, by the way. It's not anyone else's. So if it's wrong, then it's my fault, okay? Map does transformation. Filter does restriction or selection. Reduce does combination or consolidation, depending on how you want to look at it and structure it. And for each does side effect to iteration. Okay? So let's imagine this simple data flow. All right, at one end we have a source which emits data, flows into a filter. The filtered data goes into map, where it's transformed. The transformed data goes into a partition function. Anything that goes matching goes to one handler. Anything that doesn't match goes to the other handler. And why is this distributed? Well, this is clearly a data flow, but why is this distributed? It's distributed because not every operation necessarily happens on the same machine as any other. This would be a version with managed effects, which is to say that the each would produce effects, which would then go to an effect handler. You see that in a couple different emerging functional programming paradigms. So pretty much the same thing. And we already see some meager adoption. We do, right? Datalog, there's Datalog in Clojure contrib. There's DataScript, or DatScript, sorry, which, no, it is DataScript, sorry. Written in Clojure, there's the DUSA language that runs in the browser also. Distributed Datalog, there's DataHike, which seems like it would be a cool distributed Datalog implementation. Apache Spark and Apache Flink and Beam, which I know are they still popular? I don't know, but they have some data flow semantics. Some distributed data flow semantics in there, right? Really interesting things. We need more, though. We need a lot more. And the reason is, and if you've heard me and you've heard me being cranky, then you'll sort of start to get it. But this is actually part of a much larger problem that I see with distributed systems right now as a practitioner. It's just too hard. It's just really hard, right? The cognitive load, the amount of stuff you have to keep in your head is too hard. It's just too much, right? It's too much. And it requires teams and effort, and it's cost ineffective to build these systems really, really well. Some hard things about distributed systems: adding hardware can make it slower, like we talked about at the beginning. Language models don't translate to systems, like we talked about in the middle. Running them is an ops nightmare. We didn't even get there. We need to make it easier for practitioners to build distributed systems well. And because I didn't define better before, I see you, right? Because I didn't define better before, what do I mean by well? Well, structure problems to minimize coordination. That's not really easy to do. Bridge the gap between everyday languages and disorderly programming. Maybe declarative languages is a way to do it. Make application security and system reliability top-level concerns. These are really hard to do. So yeah, I'm a distributed systems specialist. It's my jam. I love it. I read lots of research. I haven't read all of it, but I read a lot. And until this gets easier, yeah, I'm going to be on Team Monolith, right? Until we, as an industry, partner with academia and some of the really cool work being done, I can tell you about that, find me after, until we can bring this stuff and make it pragmatic and make it approachable. By the way, I live in Pennsylvania. I'm from Philly. It's a big agricultural state, like I know that Illinois is and many other states are big agricultural states. I learned this really cool term that they use in the agricultural community. It's called extension. So like an extension school. So like, for example, when the spotted lanternfly invaded Pennsylvania and we were all squashing our spotted lanternflies because we're good citizens of the Commonwealth, what did we do? Well, we went online to the Penn State Extension School and we learned all about the threat that this had. And I was like, what is an extension school? And then I learned what an extension school means. It means they extend the benefits of research out to practitioners in the field, literally in the field, they're farmers, right? They extend this, and that is just awesome. We need to do extension, right? We need to get some of the things, and we need to do it in both directions. We need to see, here are some of the lessons we've learned the hard way in industry. Can this inform your research? I think that we definitely need to do that. So until this gets easier, I'm going to be on Team Monolith, right? Yeah. This has been quite a ride. Let's review. We started with cost, we went to Calm, then we went to Datalog, and from Datalog we went to Dataflow. We did a lot, and there's like a lot that we didn't really cover today, if you think about it. Because we didn't cover Amdahl's law, we didn't cover Gustafson's law, we didn't cover confluent programs, we didn't cover distributed system simulation or performance benchmarking, because even though I started off one way, it really wasn't a performance talk. It wasn't intended to be anyway. We didn't talk about the CAP and the PAC-ELK theorems, PAC-ELK obviously being an extension of CAP. They really should have called it the PAC theorem, because CAP has headgear connotations. Paradigms of parallel and distributed computing, we didn't talk about that. Do you like this sort of stuff? Yeah, so if you do, good. I'm super glad. Great, me too. Please get in touch with me. I'm dressed like this. If you find me in the halls, if you're interested in working with me, I'm always interested in new projects and I'm looking for my next thing, job, whatever as well. I really need to be honest, I love this stuff. I think it's really cool and I'm really, really glad you were here. So just thank you so much for coming.